So, I think, I just remember it's the same as like when you calculate radians, or you're looking at radians. The positive is counterclockwise. Yeah. So the effort moment would be counterclockwise. That, you would say, is the positive moment, just based on that convention. And then the resistance moment would be clockwise, which would be negative. So that's why when you add them together, they equal 0. Or you can just set them equal to each other and not care about the sign. We'll get more into the sign when we do like cross calculations. Wheels and axles are like levers. You can see if the fulcrum was like a 360-degree pivot point, then it would just be like a wheel. What does this mean? Both effort and resistance forces. If unopposed circumference. Okay, we know that. It's the same formula. If you were allowed to go in the entire way around 2 pi r. I don't know what it's talking about. We're not going to use this for today's assignment. So we'll go back to that when we have wheels and axles, or like pulleys. For actual mechanical advantage, I was talking about how it's the actual measured force divided by the effort force, the actual measured effort force. So when it's saying like static equilibrium, or when you need to, I actually don't know if that's part of today's assignment either. At some point you're going to have to say, just assume that the ideal mechanical advantage is the same as the actual mechanical advantage. So like when the question says, what force do you need to overcome static equilibrium, or something like that, you would get the actual mechanical advantage and set it equal to the ideal mechanical advantage, and that would allow you to calculate one of these forces. We'll see that in the assignment. If you get stuck, we'll talk about it. That's just calculating, just using that formula. It's really, really simple. So the ideal mechanical advantage would use the distance, just the distances. The actual mechanical advantage uses the forces. You would be setting those two equations equal to each other. And if you had 3 out of the 4, then you could solve for the last one. That's what we'd be doing. We would be doing. Questions so far? You haven't really seen any examples, so it's this is a good question. Why is the mechanical advantage, or the actual mechanical advantage, smaller than the ideal mechanical advantage? What do we say for ideal mechanical advantage? What are we doing when we talk about ideal mechanical advantage? We are using distance, but what? Say it again? We're ignoring friction. So when we calculate the ideal mechanical advantage, we're saying that everything's perfect and nothing rubs and all the forces are clean. But when we actually measure it, we do have friction, we do have atmosphere, we do have everything. So the ideal mechanical advantage usually, well, always, actually I think it's always higher than the actual mechanical advantage. Efficiency, the equation for efficiency is just dividing the two, finding the ratio between the two. Your actual mechanical advantage should be smaller. And then you consider the ideal mechanical advantage as like your 100%, and then you divide the two, multiply by 100, and you get the percent efficiency. The closer you are to 100%, the more efficient your machine is. I mean, that should make sense. When we do our design problem, you'll be calculating the ideal and actual mechanical advantages for each component, and then at the end you'll calculate your efficiency. You would just divide the two and then multiply by 100, right? So 2.44 it would be on the bottom, and then 2 would be on the top. 82% efficient. No machine is 100% efficient. And that's it. We're not going to talk about wheels and axles yet. Any questions?